Yeah, thank you. Can you hear me?
Yep.
Yeah, okay. So first of all, I want to thank the organizers for inviting me to this virtual expedition. I must say that I'm not really in algebraic combinatorics, rather in enumerative combinatorics. There's some echo. What should I do here? I'm not sure. Okay, I guess I live with it. And so one of the reasons why I'm very pleased to being here is that I think that in these days of global warming, it's important to have such meetings. So what I'm going to present is recent work on a new partial order defined on Dyck paths. And this was done with Jean-Luc Baril, Sergey Kirgizov, and Mehdi Naima. So what you'll see in this talk is a new family of lattices indexed by some size n. We will be able to count pair intervals, and we will then consider interesting sub-posets. And finally, we'll conclude with an unexpected connection with a certain congruence on words called the sylvester congruence. So I will begin with two orders defined on Dyck paths. And first of all, I will recall, if needed, what the Dyck path is. So it's a sequence of up and down steps that starts and ends at height 0 and never reaches a negative height. The size of a Dyck path is the half length. That's the number of up steps. And some important factors are the so-called valleys, that is down-up factors. Here you have two valleys, and on an up-down factor would be a peak. So many posets have been defined in the past on Dyck paths of size n, but today I will focus on these two, so the classical Stanley lattice and the new ascent lattice. So let me begin with the Stanley lattice. It's nice to describe it using its cover relations, so the minimal order relations. And to define them, so you pick a Dyck path P, you choose one of its valleys, and you flip it into a peak. So you swap the down step of the valley with the up step that follows it. So the new path Q is a bit higher than P. And in fact, this gives an intrinsic characterization of this order, namely P is less than or equal to Q if and only if P fits below Q. I don't know why Q is missing. Here's an example. So in size 3, so this is the smallest path. So say here, for instance, you see there's a single valley. If you flip it, you end up here. And if you flip this one, you end up here. So this is nicely graded, in fact, by the area below the path. And there's also a nice lattice structure. That is, every pair of paths has a supremum and infimum. Now, let me move to the new poset called the ascent poset. It's also described by its cover relations. And this time, when we choose the valley of P, as before, what we do is that we swap the down step with the whole ascent that follows. So it can be here with the two steps. So here is where we get. So you see, this would be also obtained by applying two cover relations in the previous Stanley lattice. So in a sense, this is a greedy version of the Stanley lattice. So here are two examples in size 3 and 4. So if we look at this picture here, so beforehand in Stanley's lattice, we were going from this path to that one. But now in the ascent poset, we swap this down step with the whole ascent that follows, and we jump directly to this maximal path. In particular, this is no longer graded. For this poset as well, we have an intrinsic characterization, which tells you that P is less than or equal to Q if and only if two conditions hold. the first one is expected. You want P to be below Q. And you also want a second condition that deals with the descents of Q. So here you have these 3 descents. They lie on certain, say, diagonals or lines of slope -1. And the condition is that on each diagonal where you have a descent of Q, you must have as well a descent of P. So the condition comes for 3 here in the final diagonal because every path ends with a down step. So this is why you have this light blue. But here and here, the conditions are meaningful. So for instance, if you replace P by this dashed path here, the green path has no descent on this diagonal, and so the new P would not be less than Q. So this characterization is useful in many things, like proving that these ascent posets, they are in fact lattices as well. And what I will describe in greater detail is a recursive construction of intervals in these posets in order to count those intervals. So you all know what an interval is. In fact, I will really consider intervals as pairs PQ, where P is less than or equal to Q. So I come back. So this is again the characterization of the ascent order. And one corollary is that if you have an interval, PQ, and if in P and in Q, you delete the last peak, the last up-down sequence, so you will move this final descent one step to the left, like here. Well, in what you get, the descents have basically not changed. You have created certainly a descent on what is now the last diagonal, but clearly, using this characterization, this new pair of paths forms a new, smaller interval. Now the question is how to go backwards. That is, you want to start now from an interval with, say, final peaks at heights A and B, and you want to describe in which way you can insert a new peak, both in P and Q, at heights, say, A prime and B prime, so as to obtain a longer, bigger interval. So first, there are some obvious conditions. For instance, so this new green peak you can insert at minimal height. This would be at height 1. And the highest you can go is at height A plus 1. And same for B prime. Now you want the conditions to hold, so the green path should be below the blue path, meaning that A prime cannot exceed B prime. And then you have to check the interesting condition, namely that every blue descent is also a green descent. So you see on the left of the path, not much has changed. The only place, the only diagonal you have to pay attention to is this one, which is now the next to last diagonal, because if A prime is maximal, that is equal to A plus 1, so you have created your new peak here. I hope you can see my mouse. Then there's no longer a descent on this line. And so B prime should be maximal as well. So this is this final condition. So what we are really doing is that we are constructing intervals of size n, starting from the smallest interval of size 1 that consists of 2 peaks, just by keeping track of a pair of parameters, A and B, that can evolve in a certain way prescribed by these moves here. So for instance, this move from AB to A plus 1, B plus 1 is the maximal move here. So really we have like a walk in this octant. And since I prefer quadrants, I perform a little linear transformation here, which moves me to coordinates ij. And so now I'm the steps are below and to the left of these two dashed lines. So what we're really saying here is that there's a simple bijection between intervals of size n and walks in the quadrant that start at 0, have length n-1, there's a little shift here, and consists of such steps. So we wanted to count the intervals, so now we want to count the walks, and classically we'll do so by introducing a certain generating function, so which counts all quadrant walks by the length. So there's a variable t recording the number of steps. And then you have additional variables x and y recording the coordinates of the endpoint of the walk. And then this bijection tells you that what you want is the value of this series at 1, 1. That is, you want to ignore this up to a shift. So, well, these walks, they have a simple recursive structure. You can construct them step by step by describing what are the allowed steps once you stand at ij, and this will result into a recurrence relation or a functional equation for this series. I will not show the details of the calculation, but I'm sure that if you sit down for a few minutes, you'll end up with these equations. So it expresses the main series q of x, y, which depends also on the size variable t, in terms of q of xy, but also some specializations, q of yy, q of x1, and q of 1. So maybe you're not very happy with this equation, but in fact it resembles a collection of equations that have been much studied in the past 15 years that also count quadrant walks, but with finitely many allowed steps. And more precisely, you want these steps to be small. And that is what you do is that you fix a subset of these 8 steps and count walks in the quadrant that use exclusively this subset of steps. And I promise that this gives rise to equations that look a bit like this one. And so many people have worked on such equations to understand the algebraic and differential properties of their solutions. And by taking inspiration of some of this work, we've been able, in fact, to solve this. And in particular, to prove that this series, Q of 1, 1, that we are after, is a fairly simple algebraic series. By this, I mean that you have a polynomial in the series and in the variable that vanishes. And one way of writing this consists in introducing this series Z that satisfies a nice cubic equation. And then G can be written as this polynomial in Z. In terms of asymptotics, we have an exponential growth with an explicit value of mu, corrected by a slightly unusual power of n. Okay, so this is the counting part, and I will not give more details about that. What I will do is discuss some sub-posets of my ascent poset obtained by considering only the so-called m-Dyck paths. So let me define that. So I fix some integer m, say 2. And I say that the Dyck path is an m-Dyck path if each ascent has a length that's a multiple of m. So you have an example here. To make things clearer, I have omitted every other vertex on the ascents. Now we also have mirrored Dyck paths. You probably guess what they are. Every descent has a length that's a multiple of m. So clearly such m-Dyck paths only exist if the size is a multiple of m, say m times n. And what we want to do is to take the ascent poset of size m by n and look at the order induced by the ascent order on m-Dyck paths and also on mirrored m-Dyck paths. So I'll take an example. Say m is 2, so all ascents in an m-Dyck path have even length. And say n is 2 as well, so the total size is 4. So here is my ascent lattice. Here is the smallest possible m-Dyck path, which consists in a sequence of pyramids of height m. And now if you remember the cover relations in my ascent order, they are obtained by swapping a down step with the whole ascent that follows. And so this means that any path that's above an m-Dyck path will always be also an m-Dyck path. This condition is preserved. So in other words, the m-Dyck path in my ascent lattice, they form an upper ideal. And in addition to that, it's not hard to see that there's a single minimal element. So for each n, these m-Dyck paths, they form an interval, and in particular, a lattice. So we have nice sub-lattices hidden in the ascent lattice. Now we can look at the mirrors of m-Dyck paths. Things are not as nice because the cover relations, they do not, they perturb this property of having now descents of even length. But still, you have some induced order. You see you have even here several minimal paths, but still it's a joint semi-lattice. You still have suprema. Okay, so we have tried to, now we have two parameters. We have the m and the n, and we have tried to count intervals again in these m-Dyck ascent lattices. So we obtained two families of functional equations. So first for m-Dyck path, using a kind of last peak decomposition as before, we obtain a functional equation for a new series that should be a Q indexed by M in a sense, that resembles really what we had before. Beforehand, M was 1. For the other sub-poset, mirrored m-Dyck paths, we perform instead a kind of first peak decomposition leading to this functional equation. So at this stage, of course, we would like to solve these equations, and we were not able to do so. What we were able to do is to obtain precise asymptotic estimates for the number of intervals in all these posets. And the form of these estimates is very interesting because it implies that when m is larger than 1, you cannot hope that the generating function of intervals will be algebraic, nor even what we call D-finite, which means that they satisfies a linear differential equation. And the reason for that is a result that I find very nice. So I have one slide for this. So this deals with the m-Dyck ascent lattice. So again, we have a bijection with walks in a quadrant. And using probabilistic results by Denisov and Wachtel, we were able to prove that the number, or m fixed, the number of intervals of size m times n grows exponentially like mu to the n, with a correction by a power of n into the alpha, where alpha is this beast. Okay. Now, there's the very nice result I want to mention tells you that the corresponding generating function can only be D-finite, and in particular algebraic, if this alpha is a rational number. The question, is this alpha rational? Is this arc cosine a rational multiple of pi? Or is this C the root of a Chebyshev polynomial? And we could prove that this is never the case when m is larger than 1. So alpha is irrational, and the series will not be D-finite nor algebraic. And so this results on the rational values of alpha using the theory of so-called G functions, which is something very deep and more on the arithmetic side. So this negative result is in contrast with, for instance, the m-Tamari lattices, that's another lattice on Dyck paths, and m-Dyck paths, where intervals have an algebraic generating function for any m. Okay, so this concludes somehow the enumerative part. And I want to finish with an unexpected connection with this sylvester congruence that was invented by Hivert, Novelli and Thibon some 20 years ago. It has nothing to do with the mathematician Sylvester, but rather with the silva, meaning forest in Latin, as you can see. So we were counting intervals, we had functional equations, so we had sequences. And we looked at the online encyclopedia of integer sequences and realized that the numbers of intervals for mirrored m-Dyck paths appeared in the OEIS. So for instance, when m is 1, so that's our basic problem with an algebraic generating function, well, this appears as the number of Sylvester classes of one multiparking functions. Okay. Same when m is 2, with 2 multiparking functions, and so on and so forth. So there was a little mystery to understand here, or to explain. And so I will first tell you what is this Sylvester congruence. So it is defined on words with integer letters, and it's generated by commutation relations, which are the following. So if you have a small letter A followed by a large letter C, and somewhere further to the right, you see a B that is in between in this precise sense, then you can commute A and C. And then it's not so hard to see that in every equivalence class or every commutation class, there is a single word called Sylvester word, which avoid all possible subwords of the shape ACB with these conditions. So I insist that these are subwords, so you don't require A and C to be neighbors, which was the case here. Let's look at an example. So here's a word. Here you see that you have one of these patterns, A, C, B. So you can swap 2 and 4. Now this is probably not the end of the story. You have 2, 5, 3 of the same shape. So you can swap 5 and 2. And this one has no more subword of this shape. And so it is one of these Sylvester words. Okay, so now we know what is a Sylvester word, and so where are intervals in our ascent process? Well, in fact, what we gave is a general bijection between Sylvester words and intervals of a larger and more general poset, of which our ascent posets turn out to be sub-posets. So let me introduce now this larger poset, which was recently defined by Nadeau and Tewari. So again, you have a poset for every size n. Its elements are non-increasing sequences of integers. So for instance, 10, 10, 8, 8, 7, 3. And we like to represent them by horizontal steps at height 10, 10, 8, 8, 7, 3, or the green word. And the definition of this NT order is the following. U is less than V if Well, U lies below V, that is UI is less than VI, so these green steps should be lower than the corresponding blue steps. And guess what? Every descent of V, like here between 10 and 9, here, so these are the two descents of V of the blue path, should be also a descent of V. So if you remember the characterization that we had for the ascent order, and if you turn your head a little bit, and finally encode Dyck paths by non-increasing sequences between 1 and n. Well, and if you chew this a little bit, you will realize that our ascent lattice is just an interval in this more general NT lattice with some simple minimal and maximal elements. Okay. Now, what about congruence classes and sylvester words? Well, I don't have time to give details, but we found an explicit, not too complicated, but not too obvious bijection between sylvester words on this alphabet containing the letter 1. You have to fix them in a way. And intervals in the Nadeau and Tewari lattice of size n, where U and V have positive entries and they must coincide on the same first letter. Okay, there's an example here, but I'll skip it. And I promise that if you specialize this to the intervals that come from the ascent order on m-Dyck paths or on mirrored m-Dyck paths, you can describe the corresponding sylvester words. And this is this class that we found in the OEIS. Okay, so I have some questions to conclude. I will not describe all of them, maybe the first and last. So one natural question is that we've found this algebraic generating function for intervals in the original case where m is 1. Our proof is highly non-combinatorial. We just play with functional equations. So it would be nice to find a more combinatorial proof of the algebraicity or maybe of this nice recurrence relation. We have no idea whatsoever how to prove this. And at the other end of my slide, something that we've not discussed at all are topological or geometric properties of these posets. Maybe some of you could be interested in that. Okay, I stop here. Thank you for your attention.
Right, thanks. Let's thank the speaker.
So am I doing something wrong
Questions
for
for
having
Mireille?
such echo?
I don't think the echo is coming from you. There is a like a background noise that is coming, I think, from your maybe your headphones. But Foster, I think you are the one with the echo. Yeah, Mireille, you are the one with the background noise. But there are also some echo. So Nathan, go ahead with your question.
Yeah, so thanks for a very nice talk. There's no, these lattices are not ranked, as you told us, they're not graded, but it seems like there's a natural notion of sort of a size of interval, which would be the difference in the number of descents between P and Q. You know if there's any nice enumeration, nice refinement of the enumeration that counts these intervals according to that size?
So the quick answer is no, I don't think there is any result because this is a new process which has not been studied very much. So you said the difference between the number of ascents.
The number of so in your post, I guess for P to be less than or equal to Q, there needs to be a containment, and then also what every descent of Q needs to correspond to a descent of P, but P might have more. So perhaps the difference in the number of descents would be a statistic on these intervals.
Could be. So if we think of the Tamari lattice, so one interesting additional parameter is the longest chain between P and Q. And for this, there are equations and nice conjectures, as you probably know. So maybe that would be also a variant of this. It would be a different parameter. Okay, so Cyril is asking something in the chat. Cyril Banderier. Is there a larger class with n to the -7, or is this just an accident? So that's a question I thought of. So Cyril is referring to this asymptotic behavior of intervals being in mu to the n to the -7 halves. And what you see when you count trees is n to the -3 halves. When you count planar maps, you have -5 halves, but 7 halves is more seldom. So a quick answer would be that this corresponds to maps that would be n-rooted. But if you think of the corresponding walks in the quadrant, if you want, you can deform this quadrant so that your walk has no longer correlations between the vertical and horizontal projections, and then you have an angle that is really 2 pi over 5. And really this exponent is related to, say, the Brownian motion living in a cone in a wedge of angle 2 pi over 5. So that's one question. That's one answer. Sorry.
Okay. Okay. There's another one.
Spencer Beckman, to clarify, do you expect that the Hesse diagram of the ascent order can be obtained from the one skeleton? I don't know. This is related to my final question. I have to confess that I'm not used to thinking in those terms. Yeah, I don't know. That would be interesting. Thank you.